everyone, today I'm excited to present our work for ultra-high resolution matting. This is an overview of our method. Our motivation comes from the limited hardware resources of consumer-level GPU or mobile devices. Existing methods cannot process UHR matting in one shot at full resolution on the limited memory. Additionally, existing techniques for UHR matting often produce unexpected artifacts. We propose a computationally efficient approach, SparseMat, based on the observation that AlphaMat usually consists of a lot of solid regions which can be skipped. In SparseMat, we use a spatial temporal sparsity map to indicate active pixels and thus skip those inactive pixels during processing. Experiments show that with our SparseMat, the computation is cut off by more than 19%. One of the main challenges of UHR matting is the limited hardware resources of consumer-level devices. For example, while high-end GPUs like NVIDIA 1080 Ti have 11 GB of memory, mobile devices typically have only 4 GB or 6 GB of RAM. This makes it difficult to process UHR images and videos in one shot at full resolution using existing methods. Typically, existing methods can only handle resolutions up to 1920p, which is far below the resolution of UHR images and videos, which can be 4K or higher. Moreover, to avoid out-of-memory issue, existing techniques such as super resolving and patch-based methods often produce blurry and seamed artifacts. For UHR matting, we have three observations. First, UHR images consist of a lot of solid pixels, and thus a large amount of computation may be wasted. The second observation is that solid region does not require high resolution input, where working resolution at 512p is sufficient as shown in the figure. The last observation is that two neighboring frames usually share a lot of color pixels, which can be skipped. These observations motivate us to construct a sparsity map used to guide the model to only focus on valuable pixels and ignore those essential pixels. In our method, we use a sparsity map to indicate active pixels in the image or video. The sparsity map is a binary map where active pixels are marked as 1 and inactive pixels are marked as 0. By using this map, we can skip the processing of inactive pixels. The sparsity is defined as the ratio of inactive pixels to the total number of pixels. A higher sparsity means that there are more inactive pixels in the image or video, that is, less computation is required. Given a sparsity map, we can apply sparse operations to process these irregular pixels. In traditional convolution, tensors are stored in a contiguous block within memory. This works well for dense data like images, but not feasible for sparse data. Sparse convolution is proposed to address this issue. In sparse convolution, tensors are stored in hash table for quickly indexing. We build up our method SparseMat based on the sparsity map and the sparse operations. Our method SparseMat consists of two steps. Step 1, construction of the spatial temporal sparsity, and Step 2, a sparse high-resolution module. Spatial temporal sparsity has two sources, spatial and temporal sparsity. Spatial sparsity is built based on low-resolution prediction, which is generated by a low-resolution prior network. To incorporate more context information, we apply a dilation operation on the output of the L pin. The dilation kernel is set to 15 in our experiments. Temporal sparsity is built based on the color difference between two neighboring frames. By identifying pixels that are similar between frames, we can skip processing those pixels in subsequent frames. The spatial temporal sparsity is the intersection of spatial and temporal sparsity. Through our experiments, we found that spatial sparsity alone can reduce computation cost by 90%. With the addition of temporal sparsity, we can achieve even greater reductions in computation cost. After we obtain the spatial temporal sparsity, we apply a sparse high-resolution module to process active pixels. The architecture of SHM consists of an encoder-decoder structure and a masked SE layer. Masked SE takes the channel attention for foreground and background information separately. This allows us to focus on the most relevant information and improve the accuracy of the format. The sparse output from SHM is then converted to a dense representation through a sparse-to-dense operation. With our sparse high-resolution module, UHR images can be processed smoothly in a forward pass at full resolution on a 1080 Ti GPU with 11G memory. Our experiments show that SparseMat can handle up to about 4.3 million active pixels, making up for about 50% of a given 4K image. To deal with images with small active pixels, we can adopt a cascading inference. In summary, we simply apply the sparse high-resolution module in a cascading manner to progressively reduce the number of active pixels. In this example, the number of active pixels is more than 9 million without cascading. Through cascading, the number of active pixels is reduced to about 4 million. The sparse high-resolution module can be applied with different low-resolution point networks. This allows us to use different networks depending on the specific application and achieve optimal results. To evaluate the effectiveness of SHM, we compare the results with and without SHM on 3 different datasets. In all cases, we find that the matting performance is consistently improved with the use of SHM. The cross-patch contextual module is designed to address a long-range patch dependency issue, which is a common problem in patch-based methods. We compare our approach with patch-based methods that are equipped with CPC. As shown, our approach achieves superior results while using much less memory and running at a speed that is about 30 times faster. In addition, our approach also achieves better performance than deep guided filter, especially on the boundary region. We provide some qualitative results on HM2000. Visualization of the spatial sparse map is provided on the bottom left of the image. Here we visualize some examples of our method on real-world videos. Thanks for watching.